The purpose of this uh, training module is for the W900 virtual inputs, including an example of using the Disturbance virtual input. Mike and I will go through the presentation, and we hope you find it helpful. Okay, virtual inputs. Let's define what a virtual input is. You know what sensor inputs are. An example is a conductivity sensor. You know what analog inputs are. An example might be an ultrasonic level sensor that's wired into the controller. Digital inputs, same thing, contacting head water meter. All of the above are physically wired into the controller, and you program the controller to tell it that that input is a conductivity sensor, that input's a level sensor, and so forth. The virtual input has no wires. However, they can be used to control in the same manner as the physical inputs we just described. All of the inputs are found under the inputs menu in the controller. So what are the types of virtual inputs? There's four: calculation, redundant, raw value, and disturbance. And we'll go through each of these to help you understand them. The calculation, it's a type of virtual input that's not a physical sensor. It's a value that's calculated from two physical sensor inputs. And when you set up the calculation virtual type, you select from a list of defined sensors, analog inputs, flow meter rates, or other virtual inputs. You can even use the solid state relay percent output or an analog percent output. So those are your selections when you're setting up your virtual input calculation. There's four types of calculations that you can do: difference, ratio, total, and percent difference. And we'll go through an example of each of these. For the difference, you're simply taking one and subtracting another input from it. A very simple example is if you have makeup water coming into the cooling tower and you're also measuring the blowdown water leaving the tower. If you take the difference between those two, sometimes they can equate to a savings on sewer tax, because not all of your makeup water goes to sewer. If you're running a cooling tower, you know you lose some through evaporation or windage or leakage. So in this example, we have our makeup water coming into input D1 and our blowdown water coming into input D2. We go to our virtual input menu, and for calculation mode, we select difference, and then we define the input, makeup water meter, and we define input 2, the blowdown meter. You go back to the virtual input menu, and it does the calculation that we've asked it to. You take your makeup water meter, subtract your blowdown water meter value, and you end up with a difference. So just a simple calculation that you can do. The next type of calculation is called ratio. You take one input and you divide it by another input. Many water treaters use this to calculate cycles of concentration, which you know is defined as system conductivity divided by makeup conductivity. So we look at our inputs menu. In this case, we're measuring makeup conductivity coming into input S11, and system conductivity is measured going into input S13. So we go over to our virtual input menu, and this time we select calculation mode, we select ratio, and cycles of concentration has a numerator. In this case, that's system conductivity, so that's our input, and the denominator is makeup conductivity. So in this case, it's input 2. Back to our virtual input menu, you can see our input system conductivity is 1664. Our makeup conductivity is 309. The virtual input menu does the calculation, and the result is 5.39 cycles of concentration that the cooling tower happens to be operating at. So that's an example of using the ratio. The next type of calculation is called total, and it's just as described. You take and total them. Sometimes customers want to know the total amount of water that's coming into their cooling tower, and often they'll have two sources, city water and well water. So in this case, we go to our inputs menu, and our city water meter is connected into D1, our well water meter is connected into D2. So we go back to our virtual input menu, we select total for the calculation mode, we identify the input of city water and input 2 of well water. Back to our virtual input menu, it does the calculation we've asked it to. It adds up to 2 water meter totals and gives you a total of 2,000 gallons. So pretty simple. The last calculation that you can do is called percent difference. And the example we show here is percent rejection in reverse osmosis applications. So this percent rejection is a calculation used to express how well the reverse osmosis unit is working. And it's determined as follows. You take the TDS of the feed water, and then you subtract the TDS of the permeate. The permeate is the water that comes out of the RO unit's faucet. And that's divided by the TDS of the feed water, and the whole thing gets multiplied by 100. So it's simply an equation that we're asking the controller to do for us. So here, city water is 309 microsiemens, the RO water is 16. You do the calculation, and you end up with 94.8% rejection. You go to the inputs menu, and here our city water conductivity comes into input S11. The RO water in this case is coming into input S13. We go to our virtual input menu, select percent difference. We identify the input as city water, and we identify input 2 as the RO water. Go back to the virtual input menu, and it does the calculation that we've asked it to do, ending up with 94.8% rejection.
Now I'm going to talk to you about the redundant virtual input. And what the redundant virtual input is, it's a value that's calculated from 2 physical sensor inputs. So the redundant is not a physical input, it's a virtual input. The algorithm compares the readings from the 2 sensors, and it chooses which sensor to use. And the input value that's displayed is chosen by this comparison. You can see down there we're comparing the 2 sensors, and we choose sensor S11 to display on the redundant sensor input. There are 3 modes for redundant sensors. There's the primary backup mode, and the primary sensor is selected as the input value as opposed to the backup sensor, which is input number 2. It's chosen as a virtual input value, assuming it has a valid reading. The minimum value, if the failing sensor normally drifts high, then you choose minimum value. And what that means is the sensor that has a lower reading is chosen as a virtual input value. For maximum value, if your failing sensor normally drifts low, you choose the maximum value. And the sensor that has a higher reading is chosen as a virtual input value. Now, in any of these cases, if one of the sensors goes into a range error or false alarm, the other sensor takes over. For all 3 modes, there's a deviation alarm. So you can set a difference between the 2, and if the deviation amount, and if the difference between the 2 sensors exceeds that programmable amount, a deviation alarm is set, but control continues. For the next examples, we're going to have 2 pH sensors. We have pH sensor S11 and pH sensor S13. For primary backup, under the virtual input, redundant is selected as type. The primary sensor is selected as input, and the backup sensor is input number 2. For min and max values, the sensor that has a lower reading of the 2 sensors is chosen as a virtual input value. That's for the minimum value. So this makes sense if the failing sensor normally drifts high. So you can see in this example, the pH sensor S11 has a lower pH value, and it is chosen as the redundant sensor input value. For maximum value, which is the opposite, the sensor that has a high reading of the 2 sensors is chosen as a virtual input value. Remember, you use maximum value if the failing sensor normally drifts low. Recapping redundant sensors. If the difference between the two exceeds a programmable amount, a deviation alarm is set, but the control continues. If one of the sensors goes into a range error or false alarm, the other sensor will take over. And if both sensors give invalid readings, an alarm input is set and any outputs, any controls using that virtual input are disabled. The next is virtual input is a raw value virtual input. Now, what is a raw value virtual input? It's not a physical input, but it's a value that comes from an unmanipulated, uncalibrated signal from a real physical sensor. So what can you use this for? You can log, graph, or control based on a sensor's raw value. For conductivity, the non-temp compensated value is in microsiemens per centimeter, and for pH, ORP, disinfection, generic, or copper nickel, the raw value will be displayed in millivolts. And temperature, the raw value will be displayed as ohms. And this can also be helpful for troubleshooting. So you see here, these are the different sensor input types. You have the pH input, and you have S11, you have a value, a pH value, and then you see the raw values in millivolts. On the conductivity sensor input, you see microsiemens per centimeter as the value and also as the raw value. And the raw value, again, is the unmanipulated, uncalibrated reading. For the free chlorine, which is a disinfection sensor, parts per million is the value, but the raw value is in millivolts. The pH sensor measures in millivolt units and converts to pH units. So for every pH unit above 7, the millivolt value should change for about negative 59 millivolts. So at a pH of 9, you should expect to read negative 118 millivolts. For every pH unit below 7, the millivolt value should change by about positive 59 millivolts. And at pH of 4, you would expect to read plus 177 millivolts. So if you have your handheld pH meter and it's reading a pH of 8, then at a glance, you know the sensor should be reading, the raw value should be reading about negative 59 millivolts. If it's not, then you know something is wrong. Disinfection sensors read in millivolts and convert to parts per million. And there's a slope associated with each sensor range. For example, the 0 to 2 parts per million free chlorine sensor has negative 1,000 millivolts per parts per million. The 0 to 20 parts per million sensor has negative 100 millivolts per parts per million, and so on, up to the negative 2,000 parts per million free chlorine sensor, which has a slope of negative 1 millivolts per parts per million. So for example, if you have a 2 parts per million free chlorine sensor in the system water, you should see around 200 millivolts reading. At a glance, you know the free chlorine sensor should be reading about negative 200 millivolts. If not, you know something is wrong.
Okay, the last type of virtual input is referred to as a disturbance virtual input. And the value of the virtual input in this case is calculated from a real sensor input plus an equation that defines the real sensor's impact on a control output that is using a different real sensor. That's kind of a mouthful and a lot to digest. So we're going to break it down into a couple of examples to help you understand this. First example, very simple. If you have pH control and you're basing it on a pH sensor, but the control output signal is modified or multiplied based on a flow signal. So under normal conditions, let's say you're feeding acid based on pH, but you also are monitoring a flow rate coming into the tower. That flow rate is our disturbance. And the on-off control mode of the acid feed is enhanced to add a disturbance input that is multiplied by the user entered set point. So in other words, you're sitting there and feeding acid based upon pH on a set point, but if all of a sudden you get a high flow rate coming into the tower, you want to increase the amount of acid to that untreated water, so your set point will be multiplied or increased during that disturbance time. Another typical example is if you're doing on-off control of PTSA in a corrosion inhibitor. and that's fed based upon the Little Dipper 2 sensor. Remember the Little Dipper 2 sensor, an optical sensor, it reads the amount of dye that's in the water, and the dye is blended with the chemical and put in a drum, and there's a ratio between the ppb of dye and ppm of active product in the chemical. And so by monitoring the dye, you know how much ppm of active ingredient is in the water system. So you'll sit there and you'll measure the amount of dye and control your inhibitor feed. The disturbance input has a corrosion sensor for its input. And in this case, we're using the WallChem corrosion sensor, known by the LPR acronym, which is linear polarization resistance. So the relay uses the normal set point as long as the corrosion is okay. The higher corrosion readings will cause the set point to increase. And let's explain that a little further. So if you're feeding based upon the Little Dipper 2, the ppm value, and you have a disturbance input that you're monitoring, in this case, the LPR, the corrosion reading, what we do is we define the disturbance set point, and in this case, we call it 5 mils per year. And then we define the maximum disturbance of 9 mils per year. So we also then define a minimum value of 1 and a maximum value of 5. And what does all that mean? So at a corrosion rate of 5 mils per year, the multiplier is 1, and the relay feed ppm set point is unchanged. So if you have a feed set point of 100 ppm and your corrosion rate is 5 mils per year or less, your feed ppm set point is going to stay at 100. However, if your corrosion rate increases up to 9 mils per year, that's going to cause the relay feed ppm set point to be 5 times higher than it was at 5 mils per year. So let's look at this a little further. The Little Dipper is wired into sensor input S21, and it's reading 93.5 ppm. Our corrosion sensor, LPR, is wired into input S22, and it's currently reading 6 mils per year corrosion rate. If we go to our virtual input and we set it up as a disturbance input, and we define the LPR S22 as our disturbance input, that's our corrosion rate, we say that a minimum disturbance of 5 mils per year will give us a value at a minimum disturbance of 1. A maximum disturbance of 9 mils per year will give us a value at a max disturbance of 5. So again, that means if your corrosion rate is 5 mils per year or less, our multiplier to the inhibitor set point is going to be 1. As our corrosion rate increases up to 9 mils per year, the multiplier that we apply to the set point increases up to 5. So here in our virtual input menu, the increase in the LPR sensor corrosion rate, which is our disturbance input, when that increases up to 6 mils per year, that's created a calculated disturbance value, or a multiplier, of 2. So what happens with that multiplier? If we go to our output relay menu, and it's programmed as on-off disturbance, you can see that the normal set point is 100 ppm. However, we have a disturbance input of 2. That comes from our corrosion rate, which then causes the current set point to be multiplied by 2, creating a new set point of 200 ppm. So while your corrosion rate is up to 6 mils per year, which causes a disturbance input of 2, we're going to try to maintain a set point of 200 ppm of our inhibitor. And as the corrosion rate comes back down, gets to 5 mils per year or less, we will go back to our normal set point of 100. So the disturbance causes an increase in the set point value that the controller tries to maintain. So this is one example of using a disturbance input. The other examples we can apply are the pulse output or an analog output. So you have three things here that you're combining: a primary pulse or analog control output, a disturbance input, and now we're going to add another factor called a trigger input. And if the trigger input is active, the disturbance input is multiplied by the primary output, just like we did with the on-off relay. Okay, you're multiplying your disturbance value times your primary output set point or percent, and you're increasing your output during that disturbance period. But in this case, the trigger, which I'll describe further, has to be active for that disturbance multiplier to be applied. The other thing you can do with the trigger is you can simply switch between a primary output and a disturbance output. So you can actually change algorithms from a primary algorithm control to a disturbance algorithm control. So here's the three scenarios. If we're controlling a pump using an analog output, in this case A22, and in our menu the trigger is set to none. So in this case the trigger will have no influence on the control output. So our A21 is a PID control, and that's how we're normally controlling the pump, and our disturbance input is a flow rate. So with the trigger set to none, our A21 set point is simply multiplied by the disturbance value. And if our flow rate increases, the percent output going to the pump will increase based upon the magnitude of the disturbance value. So here now the second scenario, we're going to add the trigger in as another factor in our control scheme. So we set the trigger mode to disturbance, and our trigger input is relay 3, and it's an alarm relay. And that alarm relay will go off or energize when we have a high flow rate. So we sit here and we normally control with PID, and we have a second control algorithm, in this case A23, and that's set to proportional flow control. So you have two algorithms here, PID control and proportional flow control. And now we have our trigger sitting there. So if the trigger occurs, if we get a high flow rate alarm, if R3 goes off, then control switches from PID control to proportional flow control. So you can actually change control algorithms based upon a trigger or a high flow rate in this case. The last scenario we have is where we set up trigger to be the multiply mode. And so again, the trigger is a high flow rate, relay 3, and we have our one control algorithm using PID, and we have our disturbance input, which is a flow rate. So in this case, when the trigger is hit, when the R3 alarm activates because of a high flow rate, that is when the A21 set point is multiplied by the disturbance value. And it's only when that trigger occurs, as opposed to scenario 1 where the disturbance value always is multiplied by the set point. In this case, the trigger has to be invoked, or the R3 alarm has to be active, and that's when the disturbance value gets added into the equation and multiplied by the A21 set point output. So those are three different scenarios that you can consider using for your water treatment needs. And that's all we had. We hope you found this helpful, and we'll talk to you soon.